In previous videos, we had gotten into discussions regarding solutions in terms of them being homogeneous mixtures composed of a solute and a solvent. We said for those mixtures to form, we have to have attraction between our solute and our solvent particles, so our intermolecular forces come into play. The solute and the solvent have to have those similar strength forces to attract. And then we talked about that there's also the impact of energy in regards to those solution formations. So as we move on, we're going to get into solutions in more detail. We're going to talk about some properties of solutions. Now, before we can get into talking about properties, we need to do a little bit of review about some concentrations. So when we talk about concentration, remember we're describing the amount of solute present in our solution typically. Now, two types of concentrations you would have encountered. Your first semester chemistry class would have been molarity, represent with a capital M, moles of solute per liter of solution. And then we have mole fraction, so moles of solute divided by moles of solution. So if we look at an example, we're asked the molarity of a solution prepared by dissolving 6.864 grams of potassium permanganate in 265 grams of water. We're asked for the mole fraction as well, and we're told to assume the density of the solution is 0.955 grams per milliliter. So we've got a lot of information there. One of the keys to solving solution problems is to know your solute, solvent, and solution. That is just a good habit to get into. Identify what is what. So remember, your solute is what is being dissolved. So we're told we're preparing the solution by dissolving potassium permanganate. So that makes that potassium permanganate my solute. It's being dissolved in water. So that makes the water my solvent. And so my solution is the mixture. It's the solute plus the solvent. So my potassium permanganate plus my water. Now, once we've identified what's what, we want to identify what information we have along with what information we are looking for. So the first thing we're asked for is the molarity. So what we know is the definition of molarity. Molarity is moles of solute per liter of solution. Where in this particular case, our molarity is going to be moles of our potassium permanganate. We identified that as our solute per liter of solution. So again, that's that total potassium permanganate plus the water. So in terms of our solute, we know the mass of the solute. In order to calculate our molarity, we're going to need moles of the solute. So remember from your first semester chemistry class, there's a relationship between mass and moles. And that relationship is the molar mass. So we need the molar mass of potassium permanganate. So we go to our periodic table, we add up our masses, and we would get a mass of 158 grams per mole. So we can write that in this equality format because those grams per mole tells me how many grams I have in 1 mole of that substance. Now we're going to use this equality to set up our unit conversion. We're going to use our factor label method or dimensional analysis. And when we do that, we start with our given information. So whoever's mass, volume, amount, we know. And so we know the 6.864 grams of potassium permanganate. We've got to multiply it by a conversion factor. So that's what we're multiplying by here. And that conversion factor, that's that relationship between what I'm given and what I need. We need to set this up so units cancel. So we start off with grams in the top of our fraction. So when we set up this unit conversion, we need to have the grams, the 158 grams on the bottom, with the 1 mole on the top. So we're going to multiply through. We're multiplying the 6.864 by 1, and then we're dividing by 158. The grams cancel, leaving us with moles. So we'd get 0.04334 moles of potassium permanganate. So we've got the first bit of information we need in order to calculate our molarity. Now, in terms of our solution, we're not given direct information about the solution, but we do know the mass of the solute and we know the mass of the solvent, which means we can get our total solution mass. So my solution mass is my solute mass plus my solvent mass. So we were told we had 6.864 grams of solute and 265 grams of the solvent, the water. So that gives me a combined amount of 271.9 grams of solution. Now, our molarity, we need liters of solution. So we need the volume of our solution in order to determine molarity. We have the mass of our solution. So again, we've got to remember these relationships. We can convert that mass to volume using density. Density is the relationship between a substance's mass and its volume. So we're going to convert the grams of our solution to volume using that density. So we're going to start off the same way. We're starting off with our known amount, which was that 271.9 grams of solution. We are multiplying by our conversion factor, which is the relationship between my mass and my volume. So we were told the density is 0.955 grams per milliliter. So we can write that in this equality format. It's the grams in 1 milliliter of solution. So when I set this up, I need to put the gram side of that equality on the bottom. I need to put the volume side of that equality on the top. My grams of solution cancel, and I'm left with milliliters. So we're taking 271.9, we're dividing it by 0.955, and that would give me milliliters of my solution. We are looking for liters. That is how our molarity is defined, is in terms of liters. So the next thing we're doing is converting our milliliters to liters using the fact that 1 liter contains 1,000 milliliters. So that's going to give us 0.285 liters of solution. So now we've got the information we need. We can combine to get our molarity. We're dividing the moles that we determined by the volume that we determined, and we're getting 0.153 molar potassium permanganate. Now, can't forget our significant figures. If you need a review of significant figures, there are review videos loaded in our online course. Our significant figures, remember those are coming from our measured values. So the measured values here are masses. So the measured value are these grams. And density, because it's coming from this measured value. So the mass that we started with has 4 significant figures. My density has 3 significant figures. Remember, the 0 out front is not a significant figure. It's just a placeholder. So when we're doing multiplication division, we've got to go with the least number of significant figures, which is 3. So my answer has 3 significant figures. So we've answered the first part of the problem. We have determined our molarity. Next thing we're asked about is the mole fraction. The mole fraction requires moles of our solute, which we already have. We've already determined that in part A. It also requires moles of our solution. And we've got to remember that our solution is the solute plus the solvent. So we have these moles already. What we need are the water moles to get our mole fraction. So to get our water moles, we're taking the mass of the water that we're given, we're multiplying by our conversion factor that's coming from our molar mass. We're wanting to cancel grams, so we're putting the gram part of the molar mass on the bottom, the mole part on the top, and we'd have 14.71 moles of water. So now we plug all of that into our mole fraction equation. So we had the 0.04344 moles that we determined in part A. On the bottom, we're taking that amount and we're adding it to the moles of water. So we're going to get a mole fraction of 0.002944. So when talking about these concentrations, when we see a capital M, so capital M is molarity, but we need to know what that means. And it's very easy to get into the habit of just saying moles per liter, but we need to make sure we specify what. So we would have moles of solute per liter of solution. Now notice in part B of the example we just worked through, I didn't put a unit on my mole fraction. It wasn't that I forgot, it's just that our mole fraction is unitless. We're dividing moles on top by moles on the bottom. The moles cancel, leaving us no units. So next we want to determine the molarity of a solution containing 26 grams of CH3OH in 500 centimeters cubed of solution. So going through, we want to identify our solute, our solvent, and our solution. So the solution contains 26 grams of CH3OH. That is my solute. It doesn't specify the solvent. This 500 centimeters cubed, that is our total solution. We are looking for the molarity. So molarity, we're going to need moles of our solute, CH3OH, divided by liters of our solution. So looking at the information that we have about our solute, we've got its grams. So we're going to take the 26 grams and we're going to convert it to moles using the molar mass of that CH3OH. So that CH3OH is going to have a molar mass of 32.05 grams per mole. So I'm putting my grams on the bottom, the 1 mole on the top, and I get 0.811 moles of my solute. Now, the other portion we need to calculate that molarity is the volume of our solution. We've got 500 centimeters cubed. We've got to remember that a centimeter cubed is a milliliter. So 500 centimeters cubed is 500 milliliters. So if I convert that to liters, that is 0.5 liters. So combining this for my molarity, I'm taking my 0.811 moles of solute divided by 0.5 liters of solution, and I get a molarity of 1.62 molar CH3OH. Now our units don't stop with the capital M. Remember, the numbers are meaningless without units. If I just said molarity, that's meaningless as well. We need to indicate whose molarity we are referring to. So that's the molarity of that CH3OH. Now, our molarity has fraction units. And because it has fraction units, molarity is going to give us a relationship between moles of my solute and liters of my solution. And anytime I have a relationship, I can use that relationship to convert between units. So that means we can use molarity to convert between grams of solute and liters of solution. So looking at problem number 4, we're asked the volume of a 2.5 molar solution of sodium chloride that contains 15 grams of sodium chloride. So if I look at what I'm given grams of my solute. The information we are looking for is the volume of my solution. There is a relationship between mass and volume, but that's the mass and volume of a substance, of the solute or of the solvent. I don't have any density information given here. The only thing I have that relates my solute to my solution is that molarity. So we're going to convert grams of solute to moles of solute, and then moles of solute to volume. Again, these should be review. You would have seen these in your first semester chemistry course. We're going to take the 15 grams of sodium chloride. We're converting it to moles using sodium chloride's molar mass, which is 58.44 grams per mole. So I get 0.257 moles of sodium chloride. So that completes my first step here. I converted grams of solute to moles of solute. Now I'm converting moles of solute to volume using the molarity. So when I look at that molarity, 2.50 molar means that I have 2.50 moles of my solute in 1 liter of my solution. We want to set this up so those solute moles cancel. So I'm putting my 0.25 moles on the bottom, my 1 liter on the top, and I'm going to get a volume of 0.103 liters. Now with our final problem, we've got a solution in which 1.5 grams of sodium nitrate is dissolved in 300 milliliters of water. And we're asked for the molarity and the mole fraction. So my sodium nitrate is my solute. The water is the solvent. So the solution is the water plus the sodium nitrate. So we're looking for molarity. If I want molarity, that means I need moles of sodium nitrate per liter of solution. We're given 1.5 grams of solute, so we can convert those grams to moles using the molar mass of the sodium nitrate. So my sodium nitrate is going to have a molar mass of 84.99 grams per mole. So I've got 0.01765 moles of sodium nitrate. Now the other portion I need is my information about my solution. I need my solution volume. I'm given solute information and I'm given solvent information, but they're not in the same units. To add them together to get my solution total, I need the same units. So I've got to either convert grams of sodium nitrate to volume, which would require the density of sodium nitrate, which I don't have. The other option is to convert milliliters of water to grams of water using density. And water's density is a density that we are expected to know. So we've got to know that water's density is 1 gram per milliliter at room temperature. And so if water's density is 1 gram per milliliter, then that means that 300 milliliters has a mass of 300 grams. So my solution is going to be the 1.5 grams of sodium nitrate plus the 300 grams of water, which is going to give me 302 grams of solution. Now we're doing addition and subtraction here. So again, we've got to remember our significant figures. When we're doing addition and subtraction, we're looking at our decimal places. So I have 3 decimal places versus 0. We go with the least amount, so I've got to round my answer to 0 decimal places. So for my molarity, it's going to be my solute moles of 0.01765 moles divided by, can't get there just yet. So I've got grams of solution now. I need volume. And the relationship between mass and volume is density. But again, I'm not given density here. I don't have my solution density. So we're going to make a very important assumption here. I have 1.5 grams of solute compared to 300 grams of solvent. It's a very, very small amount of solute compared to my solvent. When that's the case, when we're looking at very small amounts of solute, what we can assume is that my solution density is the same as my solvent density. We can't always assume that. More concentrated solutions, that solute presence is going to impact the density. But as if it's a small concentration, which we're assuming here based on comparing the masses, we can assume that the solution density is the same as the solvent density. So if that's the case, then I have 302 milliliters of solution, because 1 gram equals 1 milliliter. So I go to divide by my volume. I'm dividing by 0.302 liters of my solution, which will give me a molarity of 0.0585 molar sodium nitrate. Now, if you're given the density of your solution, you absolutely want to use that value. Here we're making this assumption. We're able to do so because it's an aqueous solution. We're dissolving in water, and we have a very small amount of solute. You will encounter other problems like this. When that's the case, assume your solution density and your solvent density are the same. Now, the other thing we're asked for is mole fraction. So to calculate that mole fraction, we already have our solute moles. So that's going to be 0.01765 divided by 0.01765. Plus we need the moles of our water. We have 300 grams of water. So we're not using the 302, that's our solution. We need just the solvent right now. So 300 grams of water times our conversion factor with our molar mass. And we're going to have 16.6 moles of water. So we've got to be careful here. We've got multiple masses floating around. This is why it's important to distinguish solute, solvent, solution. So my mole fraction, I need my solute moles plus my solvent moles. So to get my solvent moles, I needed to use my solvent mass. And we're going to end up with a mole fraction of 0.0010 6. Now, molarity and mole fraction are just two examples of ways that we can describe the concentration of solutions. We're going to look at some other ways in later videos.